So in this lecture, we are going to cover surface defects. So we are going to discuss different types of surface or the planar defects. Uh, First of all, we'll see the external surface defects, which is basically occurring at the external surface of any body which is made of some material. And then we'll see the different kinds of internal surface defects. If we divide different kinds of internal surface defects, these are basically interface boundaries, uh, different kinds of grain boundaries like high angle boundaries, low angle boundaries, and then we'll see the twin boundaries and stacking faults. So we'll start with the external surface defects. See, we have already discussed that the outer surface or the external surface of any material, any body, is definitely a defect. Definitely a defect because the surface atoms, if you observe, uh, the surface atoms, it is not surrounded by the other atoms like what is there in the inside of the material. As you can see, if you consider this inside atom, you see that around that atom, the atoms are there, and each and every internal atoms having identical surrounding. This is what is the basic crystal structure. But if you look at the surface atoms, you see these red atoms are the surface atoms. And definitely in case of surface atom, external surface atoms, you see that only in one side there are atoms. Definitely on the other side, it is the free surface. Uh, there is no atom. That means these bonds are not present. And since these bonds are not present, uh, ideally there should be some atom to continue this same crystal structure, but this bond is not present there. So that is why these atoms are at a higher energy state. This atom is at a higher energy state because this bond is not there. Okay. So basically this amount of energy that can be calculated considering this bond energy which is shared between these two. So half of that bond energy, if you consider all the surface atoms, in that way one can calculate that what is the amount of energy at the surface, and definitely it will be larger if you compare with respect to the internal atoms. So definitely if the free energy is larger, they will very quickly come in contact with different kind of reactions. They are excited, they are not in a stable condition. Okay, they are at a higher free energy state. So surface is, which is an obvious defect, you find that they are come in contact with the atmosphere and react. And so these are the region, definitely from the point of view of the crystal, is a defect because they do not have the identical surrounding. Bonds are not there, they are having higher energy. Okay. So this is the thing that we can see. This is very obvious. We have started discussion with that. But now if we see the different kinds of internal defects, so the first thing that will come is basically the different kinds of grain boundaries. So first of all, you have to understand what we mean by the grain, and then you will understand what is the meaning of grain boundary. So if you see the pattern in this particular region, if you just consider this region that I am just shading is a grain. So here within this particular grain, you see that the atoms are arranged in a periodic fashion, so that each and every atom having identical surrounding. Okay, but within this region, if you look at this region, which I am shading now, you see again the atoms within that region are also in a regular periodic fashion, and they have atoms having identical surroundings. But if you compare between this grain 1 and this grain 2, if you compare the orientation of the atoms in this grain, if you observe, uh, the orientation you can think in that way. So these are the orientation of the atoms, right? In this grain 1, this is what is the orientation of the atoms. Whereas in this grain 2, the orientation is like this. As you can see, the atoms are oriented like this. But within a particular grain, they are having the similar kind of a structure. Within grain 2, they are having the similar kind of a structure. Okay, so this is basically grain 1. This is basically a crystal. So this is what is the crystal. So if they're having the similar identical structure, that we know is called a crystal structure. So this is what is a crystal. This thing is again another crystal. So here grain 1 and grain 2 are basically two crystal 1 and crystal 2. But when they are meeting in a material, so in a material you can see this is a polycrystalline material where different crystals are there, and they are within a particular crystal, you know, they having the regular feature, but they have different orientation if you observe. And where they are meeting, when these two grains are meeting or two crystals are meeting, their orientations are different, and that is why what you observe, that there is an angle that is formed, and this angle is what is the angle between the boundaries, we can say. Okay, and you can understand this is the angle that is formed between these two orientation, between this grain 1 and grain 2, the angle is this one. Generally, in case of high angle boundary, these angles are large. Large means it is generally more than 10 degree. Uh, okay, so if it is more than 10 degree, then it is high angle boundary. But if it is small angle, generally less than 5 degree or less than 10 degree, if you consider, if it is less than 10 degree, then it is basically mm, small angle boundary. Okay, but here in grain boundaries, that you can see here, it is a very small angle. If you compare grain 3 and grain 2, the orientation difference between these two grains are very small, so it is a low angle boundary. Okay, so you can see this is a polycrystalline material. Why poly? Because many crystals are present, and between two crystal means actually that between two different orientation. So why this is a defect? This is, first of all, is a surface defect. This is not actually a line. This is not actually a line. This is basically a surface, because ultimately the thing is a three-dimensional one. So basically this is a surface where the two grains are meeting, and that region, if you just think that region where you see the different kinds of misalignment. Misalignment means the distance between the atoms are larger. Okay, whereas if you compare within a particular grain, the distance everywhere between any two atoms is same. That is what is the property of the crystal structure, pure crystal. But here you see that near the region of the grain boundary, because two different orientation are meeting at that region, you see a lot of space are vacant. You see the distance between the atoms in this region are different. So definitely these are the regions where the free energy is high. Okay, because the distance between the atom is more or less. Okay, in both cases you know that the energy goes up, and here, and this is what is the region where the defects in the crystal happens. Okay, and this is not a line, actually this is a surface. Okay, the surface is generally in a curved surface. Okay, so this is what is the um, grain boundaries, and it can be high angle boundary or it can be low angle boundary. But generally, when we say it is a grain boundary, we mean it's a high angle boundary. But low angle boundaries are also very common, and these are formed by two ways. One is tilt, another one is twist. Okay, but before that, here is some more view of the polycrystalline material. Here you can see the grain structure that you can see in a microscope, metallographic microscope. And here in this region has been focused here. And you see that this is what is the grain A. You see the similar orientation within a particular grain. And this is the region where they are meeting, two different orientation are meeting, and this is the defective region. So these are basically the grain boundary. I think this concept is clear to everyone now. So these are the different orientation has been shown in different parts, And when they are meeting, since these different orientation are meeting, this is the region where the defects occur. So this is, remember, is not a line defect. This is a surface defect that you have to remember. Okay. Now you see that uh, the different situations, like if suppose this is grain 1 and suppose this is grain 2, and if they grow gradually and ultimately form this kind of a situation, so between grain 1 and grain 2, you do not find any difference in orientation. So actually this is not a polycrystalline in that sense. If this is the only material, so this will be a single crystal. Excuse me. So this is a single crystal. But whereas if you consider this is one grain and this is another grain, when they are meeting, you see the misalignment you will observe. So this is a result of a polycrystalline material. Okay. So material, it is possible that if you closely controlled a process by which you can create a solid from a liquid, it is possible to create the single crystal. Single crystal material, let us consider this is a bath where some liquid is there, and you are trying to solidify it in such a way that it will form only a single crystal. If it is a single crystal, definitely there will be no grain boundary. Only if it is a polycrystalline material, only if it is a polycrystalline material, then only grain boundary will come into picture. But it is very costly and difficult to prepare a single crystal. Okay. But we'll see the different kinds of properties of single crystal and polycrystalline material afterwards. But grain boundary is a term definitely related to the polycrystalline material. Okay, because in a polycrystalline material, basically different crystals, means different grains, are meeting at the grain boundaries. So these are basically the low angle boundaries, tilt and twist. Okay, these are the common ways these low angle boundaries are created. I have already mentioned these are the boundaries where you can see that the region here, in this region and in this region, and the angle of orientation difference is very small, within 5 degree. Okay, within 5 to 7 degrees. So this is a very small angle, and this is generated by two mechanisms. One of them is tilt, another is a twist boundary. So tilt is basically happens when an array of edge dislocations come one after another. As you can see, this is one edge dislocation, this is another edge dislocation, this is another edge dislocation. When they are coming one after another in this fashion, ultimately you will observe a very small tilt in one portion of the uh, material with respect to the another portion of the crystal. So a small orientation difference you will observe. So when they will align, and you know that why these things happens by the time you know that in case of edge dislocation, this kind of thing happens. Uh, this kind of a structure happens in a edge dislocation. Distance between them increased, distance between them decreased. This is the region formed, and that is the reason that if an array of such um, edge dislocations come one after another, then overall material, if you look, you will find this kind of a surface. And remember, this is not a curved surface, this is a plane surface, and that plane surface is basically this line and perpendicular to that. So this is the plane surface. This is a plane surface defect that also you have to remember. This is not a curved surface defect. Again, if you see the twist boundary again is the result of the series of uh, series of screw dislocations. If series of screw dislocation comes one after another, and then you will find this kind of a orientation difference. Like here you can see parallel orientation difference you will observe here. That is, though it's a 0 degree, but it is a parallel. Okay, so this kind of a difference, but it can be some angle also because of the series of screw dislocation. So you just remember the thing that you have to remember is the tilt and twist boundary are the result of a series of either edge dislocation or the screw dislocation. Okay. and they are low angle boundaries. Okay, and both of them are plane surface defect. Okay, not curved surface defects. Now, effects of grain boundaries on the mechanical properties are very, very important. We'll discuss much on in the material properties section, definitely. But to give some idea that boundaries are good places for fracture to occur. Already, you know, this is the defective region. Okay, so definitely the good place for the fracture to occur. Boundaries interrupt movement of dislocations since in the boundary region the free energy is very high. The atoms distance between the atoms are either large or very small. So in that case, definitely the strain fields are there. So when the dislocation tries to move within the in the slip plane, you know, within the material, when they interact with the grain boundaries, definitely grain boundary interact, because grain boundaries is basically a region of um, strain fields created because of the defects. Uh, okay, so similarly for the electrical properties is also happens, and one of the very important applications, we'll discuss it later on again, and that is the region of the grain boundaries. They are not actually the crystalline, right? uh, the region in the grain boundary where the distance between the atom is not regular. Okay, so they are like kind of a liquid like structure. Okay, so they can slip with respect to one part of the grain with respect to another part of the grain. Okay, so these sometimes degrade the material property, specifically in higher temperature and high amount of stress is applied, and this particular phenomena is called the creep. Okay, so we'll see that what is creep, and if the grain boundaries are more and more grain boundaries are present, and in that case the chances of creep will increase. But otherwise, in terms of strength, if you think that grain boundaries, if the more grain boundaries will be there, the dislocation will not be easily moved because they will be interrupted if more grain boundaries are there, right? So if dislocation cannot get out of the crystal, you know that the plastic deformation will not take place. So if dislocations are interrupted, that means you need some extra energy, extra force to move the dislocations against this grain boundary interruption. That means the material is stronger. Okay, so if the more and more grain boundaries are there, that means the material is more and more strong and hard. Okay, so okay, we'll discuss all this relationship afterwards. Now, how to observe the grain boundaries? To observe the grains, what is done basically initially, the cleaning is very important on the sample. So the sample is cleaned. That means the different kinds of grinding processes through which the sample is polished. Okay, and finally, it is etched with some chemical. Etching is a process. Here you can see after polishing. Polishing means with the help of different grinding paper. Actually, it is initially polished in a disc polishing machine. After that, finally, etching is done. Etching is a process through which we can, after etching, if we see the sample under microscope, the grain boundaries can be clearly identified. Okay, so what is this etching process? It is basically a chemical, and this chemical may be alcohol and acid solution, and different kinds of etchants are there, and they are recommended for different kinds of samples. Okay, depending if it is a steel, there is some recommendation of chemical that is etchant. Okay, so what is done actually in this etching process? This chemical is given on the surface. When the chemical is given on the surface, this chemical definitely will try to react on the surface. Now you see the surface having different grains. Okay, so and you know by the time that the grains having higher free energy with respect to the grain boundary having higher free energy with respect to the grain. So that is why what happens, the chemical reaction that takes place with the etchant, with the metal, you will find that the grain boundaries react in a particular rate, in a particular fashion, whereas the grain react in a different fashion. And that is why the surface after chemical reaction that is generated and having different refractive index, and that is why when the light reflect from those surfaces are different, and that is why it is easily possible to distinguish this grain and the grain boundaries. Okay, so these definitely help you to identify the grain size and all that if you can identify the grain boundaries clearly. Now, after this grain boundary, you have seen low angle and high angle boundary. Uh, these are basically the orientation or the rotation of one grain with respect to another, right? That you have already seen. So, in case of twin boundary, instead of rotation, it is kind of a reflection. Okay, so that means if one part of the crystal, suppose their orientation is like this, as you can see here, the rotation, you see the rotation here, if you consider, if you just consider the rotate, these are the kind of orientation. If you observe, these are the orientation, and this is a particular boundary where you see the other side of the crystal are exactly the mirror reflection of this part. So one part is the mirror reflection of the other part. If this is the situation, then it is called twin boundary. Okay, because one part is the mirror reflection of the other part. When this thing happens, then it is called a twin boundary. And you will observe this thing in different ways. This twin boundary actually created either by mechanical force or by annealing. Also, annealing means if you do some kind of a heat treatment, in that case also you will find this kind of orientation difference, such that it is basically kind of a reflection of one part with respect to the other part. And remember, this twin is another process by which the plastic deformation takes place. Okay, one of the way you have already seen that when the dislocation lines move out of the material through the slip motion, then permanent deformation takes place. That you have seen. But in that way, permanent deformation takes place. But in twin, twinning is a process. By that also, the permanent deformation can take place. Okay, and you see that in case of FCC kind of a material, you will find that the annealing twin is observed, and generally it is near the crystal recrystallization temperature. This thing happens, and in case of BCC and HCP, you will find the mechanical twins. Okay, because of the higher slip systems in case of FCC, uh, uh, because of the slip movement, that means the slip motion of the dislocation, basically mechanical deformation or the plastic deformation takes place in FCC. But because of the less number of slip system in BCC and HCP, the mechanical, that means the dislocation motion do not able to create the plastic deformation. So mechanical twin is the mechanism by which the plastic deformation takes place in case of BCC and HCP. What is slip system and all that, that I have not yet explained. That we will explain when we go to the mechanical properties again. So do not bother about that. But for the time being, you just know that twinning is a different process than the dislocation motion by which plastic deformation can take place. Okay. So here also you can see that the twinning process, here you see this is the orientation here, and here with respect to this you see it is the mirror reflection. Then again with respect to this you see another mirror reflection that is taking place. Okay, so I think this picture will give you some better idea. In actually in a 3-dimension, it will give you a better idea about how the mirror reflection is taking place. So here this is a twin boundary, this is another twin boundary. Okay, and definitely you can understand, since the orientation is changing between this portion and this portion, definitely this is the region. This is the region where the defects occur. So this is the region of the surface defect occur, twin boundary. Okay, so this is again, twin boundaries are again the plane surface defects. Remember, this is not the curved surface defect. This is again the plane surface defects. Okay, that is perpendicular to the screen through this boundary region, because you know at the boundary region it is the region where the defects occur. So for the time being, I'm not going to waste much time on this strengthening process. We'll discuss in the mechanical properties. But here you can see just kind of a stacking has been shown. Let us consider it's a FCC, you know, ABC kind of a stacking. Here you can see ABC kind of a stacking. And then because of twin, you see a mirror reflection as if occurs with respect to this. And ultimately, this happens like this on the other side. Okay. So here, this is basically the twin boundary which has been shown. Okay. Now, another kind of defect, which is so already we have seen the first kind of defect that is related to the internal defect that is related to the grain boundary, which is because of the rotation of one part with respect to another part. Second, we have seen the twin boundary, which is basically the reflection of one part with respect to other. And now this one is the translation of a particular layer with respect to the another layer. So this is related to the translation. That means if let us consider a FCC crystal is there, ABC kind of a thing. Let us consider a crystal is there, ABC ABC, ABC. This is a pure crystal, perfect crystal, no defect is there. This is FCC crystal, right? Now, suddenly, if this happens that in this region, suppose in this region, let us consider this is the region there, suddenly some thing that is say A, B, A. Let us consider these few layers suddenly entered in this region. Suddenly this layer entered in this region, or some layer get out of this particular stacking. In that case, this is called a stacking fault. Okay, so here you can see these are the layers which has been introduced between this B and C. Between this B and C, this set of layers actually introduced. Okay, so when this kind of thing occurs, it is called a stacking fault. And you know that FCC and HCP, the structures are very similar. ABC in case of FCC, and in case of HCP, you know, it is ABAB kind of a structure. So it is sometimes possible that in a FCC structure, suddenly this HCP kind of a structure uh, uh, having different properties, those are introduced. Okay, so this is very common. Stacking fault is very common in this kind of FCC HCP kind of a structure. Okay, so I think this idea of stacking fault is clear to you. Okay, so within a particular structure, suddenly at a particular region, some other layers if entered, or from a regular structure if few layers are going out. Okay, then it is called a stacking fault. That's all. Now we'll see the ASTM grain size number and the grain diameter. Okay, so ASTM indicates American Society of Testing and Material. So according to them, the grain size is designated by a number. Okay, and that is called ASTM grain size number. So ASTM grain size number is, if we call this ASTM grain size number as G, ASTM grain size number is G, then we can find out this G in a way that suppose under microscope, we are using a microscope, suppose that magnify 100 times. Okay, suppose we are using a microscope that magnifies 100 times. And if we take some area when we are looking under microscope at 100 magnification, and if we observe a portion, a sample we are observing with the help of that microscope, then what we do, in 1 inch square, let us consider this one is 3 inch and this one is 4 inch. Remember, this measurement are at 100 magnification. So 3 inch and 4 inch, that means we are observing what? We are observing 12 inch square, right? We are observing 12 inch square. But definitely, what is at 100 magnification, we have to count that within that region, how many number of grains you are observing, how many number of grains are there within that area. So you have to simply count 1, 2, 3, 4, like that. You have to count. Suppose you have observed that there are n, okay, suppose there are capital N number of, uh, let us consider there are capital N number of grains present. Okay, if capital N number of grains are present, then in one, uh, that means in 1 square inch, how many grains are present? Because in 12 inch square, if there are capital N number of grains are present, then in 1 inch square, there is n divided by 12. Atto this many number of grains per inch square. Okay. So basically the idea is in 1 inch square area, if you observe 1 inch square area, this is the basic idea. And if you look through 100 magnification, then if you find that there are, say, n number of, suppose there are n number of grains present. Okay, so if you observe 1 inch square through 100 magnification microscope, and if you count that there are n number of grains are present, then this n is equal to, if we write 2 to the power g minus 1. Okay, so this is what is the definition of ASTM grain size number. So if you just simplify, then ASTM grain size number G will be equal to what? It will be simply log of n, okay, divided by log of 2. Just you simply take log both side, and if you take 1 on the other side, it will be plus 1. So this is what is the simple definition of ASTM grain size number, where n is what? N is number of grains if it is observed under 100 magnification of 1 inch square area. That you have to remember. Okay, so in this way we can find out ASTM grain size number. So instead of 100 magnification, if you suppose take magnification is 400 in a microscope. Okay, so in that case, what you do, first thing is that you have to convert it into the number of grains in 100 magnification. That is very important. So because the definition is n is observed under 100 magnification. So if you observe it some other magnification, so what is the conversion factor that you have to multiply? You see, to convert it into 100 magnification, you have to multiply the number of grains count in that magnification m multiplied by m by 100 whole square. Okay, so you have to multiply with the magnification divided by 100 whole square. So then it will be converted into n. N means in 100 magnification, what is the count? So once you know what is n, after that you simply write this formula, that n is equal to 2 to the power g minus 1, and you can find out what is g, and g is this. Okay, so this is the formula that you have to remember. I think it's clear that how can we calculate the ASTM grain size number. Let's take one example to clear this idea. Let us consider we have observed with m is equal to 200, and we have observed some area, as you can see in this picture. Let us consider this area is 6 inch square. Okay, at 200 magnification. So first thing what we do, we first find out in 200 magnification what is the number of grains. So you just simply calculate. Okay, after just counting, you found that there are 200 grains. So 200 grains are there in 6 inch square. So first thing is you have to find out what is there in 1 inch square. So simply divided by 6, you will get this many number of grains, and this quantity is at, remember, 200 magnification. So from the definition of ASTM, first you have to convert it into what is the number count in 100 magnifications. For that, what you have to do? You have to multiply by magnification by 100 square. So once you do that, you will find out n100. And once n100 is known to you, simply use this formula to find out what is the ASTM grain size number. So finally the answer is this. So this is the simple procedure. Okay. So these kind of problems are common in exam, that you can see that it is given that this is a picture, and this picture is suppose taken at 500 magnification, which is given, and the question is find out what is the grain size number. So what you do, you take a pencil and you with a scale you just take any area of your choice. With the help of inch scale, you find out what area you have taken. Definitely that area will be known to you, and you count the number of grains. Okay, so that number of grains suppose is capital N. So what you do, N divided by A, and that will be definitely this number of counts but in M magnification. Okay, this number of count in magnification 500. Okay, so after that what you have to do, that you have to multiply this quantity to convert it into 100 magnification, right? So you just multiply this quantity with 500 by 100 square. Okay, that is m by 100 square. So once you know what is n100, then you use this formula that n100 we know is 2 to the power g minus 1. And after that you calculate what is the value of g, and that is ASTM grain size number. Clear? Now coming to another problem, here you see this problem. Here the question is determine ASTM grain size number of a metal specimen is 45. Okay, it is given that ASTM grain size number of a specimen that you have to find out. That means you have to again find out in this problem what is G. You have to find out what is G. What is given that 45 grains per square inch are measured at a magnification of 100. Since it is measured at magnification of 100, so the problem is very simple. Basically, you have been provided what is the value of n100. This value is given, which is 45. So you can easily find out what is G, because G will be log of 45 divided by log of 2 plus 1. Okay, so this is what is G. Now if you second part, look at the second part, that for the same specimen, how many grains per square inch will there at the magnification of 85x. Now the magnification has been changed to 85x, and at that magnification the question is how many grains will be there. So now in the second part of the problem, you know that what is the ASTM grain size number. Now you know what is n100, and the question is you have to find out what is n85. So what is the relation between n100 and n85? Okay, so n100 and n85, you know, they are related by n100 is equal to n85 into m by 100 whole square. Okay, so simply use this formula and find out the number of grains will be there in 85 magnification. Okay. So this problem we have already seen. Now another thing is the grain diameter. So grain diameter, you remember, is simply defined as the square root of the area of each grain. So if you can find out the area of each grain, and that is area divided square root of that area is what is the grain diameter. So how can you find out the area? So that is very simple. You have the number of grains, and you are done it with a particular area, say maybe some length and breadth you have taken. Suppose the area on which you are measuring is say A. Okay, so if A is the area, then this area divided by number of grains, if you divide, then that is basically the area of each grain. Okay, suppose you are doing it at some magnification, say 100. Suppose you are doing this at 100 magnification. Okay, so definitely the number of grains that you will observe, the area will be 1 by, you remember, you have to square it. So 1 by 10 square into that. So this will be basically the, and the square, this will be the area of each grain. Okay, this will be the area of each grain. Okay, so this is what is the area of each grain. And what is this A? This A is the total area that you have taken. A is the total area that you have taken. N is the number of grains you have observed. And here we have considered 100 magnification. If you consider say magnification M, then this will be M square. Here it is 100 magnification, so it will be 100 square. I'm sorry, it's not 10 square. I'm sorry for that. If the magnification is 100, then it will be 100 square. If the magnification is M, it will be M square. So this is basically the idea, and this will be the area. So once you know what is the area, so its diameter will be what? Square root of this quantity. Okay, so square root of this quantity will be the answer. So 1 by magnification into square root of area divided by number of counts at that magnification. Okay, so this is the technique by which we can find out the diameter of a single grain. Okay, that is often considered as one of the parameter of the grain size. Okay, so this is one of the technique. There is another technique to find out the grain diameter or the grain size, and that technique is by line method. Here you can see that in the grain structure, let us consider this is the structure that you are observing in microscope. Suppose this is the structure that is observing in microscope, and what you do, arbitrary, you draw few lines at different locations. Suppose you 1, 2, 3, 4, 5, 6. In this way, you draw few lines. Here you can see that 7 lines has been drawn on the structure, and here you see that the number of grains intersected by those lines, those has been recorded. And remember, all these lines are having the same length. All these lines having the same length, and that length here is considered 60 millimeter line. So if all the lines of the same length of 60 millimeter that has been taken here, and you just count the number of cut in the grain boundaries. Okay, so here in the first line you can see there is 1 cut, another cut, so 2 cuts. So you write 2 in that way. Okay, so from a structure you just note down the number of grains inserted, and then you find out the average of this number. Find out the average of this number. Since all the lines are same, so average will be simply average of all these numbers. So it has been observed, say 9.1 is the average. Okay, if 9.1 is the average grains it cut, then what is the average, in that case, the length of each line divided by this average number of cuts, average number of grains inserted or intersected. So that is divided, and you will get some average value. Okay, so finally, if it is done with certain magnification, that you have to divide, that's all, and you will get the diameter. Okay, so this is the result of the grain diameter, but you are doing probably at say 200 magnification. Okay, so in that case, your answer will be this divided by 200. This is what is the idea. Suppose you are doing it by at 100 magnification, so you have to divide it by 100, and finally that will be the grain diameter. So this is another technique by which you can calculate the grain diameter. This is called the intersection method. Okay, line intersection method. There are other techniques also, like drawing different circles and doing in the similar way, but these are certain very popular methods. Now, finally, how grain size influence strength of the material. Already I have mentioned that the grain size, if they are fine grain materials having more grain boundaries, right? So if the material is fine grain, you see, if the material is having fine grain, that means each grain size is very small, fine grain material. Okay, fine grain material means each grain size is very small. So that means the grain boundaries are more, right? The grain boundaries are more. This is a fine grain material, fine grain structure. Whereas a coarse grain structure is what? Coarse grain structure. Uh, Coarse grain structure, that means each grain is large grain size. So if the grain size is large, now if you compare that fine grain and the coarse grain, which one having more grain boundaries? Definitely in case of a fine grain structure, having more grain boundaries. More grain boundaries means more defects, more strain fields. So it is very difficult to move the dislocation. Dislocation movement, you know, is interrupted by the grain boundaries. And dislocation movement is responsible for the plastic deformation, you know, because when the dislocation move out of the crystal, permanent deformation takes place, plastic deformation takes place. So if the plastic deformation is difficult, that means the material is hard. If the plastic deformation is easy, that means the material is ductile. So what we can conclude, that in case of a fine grain material, there are a lot of grain boundaries, that means a lot of interruption for the dislocation motion. That is why fine grain material having better mechanical properties. So fine grain material are very strong, very hard materials, whereas coarse grain materials are basically the ductile materials. Plastic deformation is easy, less interruption of the dislocation motion, in simple words. Okay, we'll discuss on this later on, but till now, uh, this much is sufficient. So thank you. And here we ends the chapter, uh, imperfections in solids.